Hello and welcome to the presentation of our Interact technical full paper. My name is Enes Yigitbas and I am a researcher at Paderborn University. Today I am going to present our work on simplifying robot programming using augmented reality and end-user development. This is a joint work with my colleagues Jovanovikj and Gregor Engels. Let's start with the motivation of the problem. Robots are becoming ubiquitous and they are used nowadays in different settings with typical application domains like education, household, or industry. They come in diverse forms and shapes depending on the tasks they were designed for. In the manufacturing industry, for example, an increasing number of robots are used for assembly tasks such as screwing, welding, painting, or cutting. Tasks are domain-dependent as different contexts of use demand different precision and safety regards. Describing a task requires process knowledge as well as domain knowledge. Transferring this as an executable movement to the robot demands programming proficiency. However, robot programming is a complex and time-consuming task where programming errors may occur. On a real robot, these may cause hardware damage up to irrecoverable damage to a person. Thus, the reduction of errors and their prevention is important. Consequently, different challenges exist which cause the high complexity of robot programming. Based on an extensive literature research, we have identified the following major challenges. The first challenge, C1, deals with program state visualization. In robot programming, the visualization of the robot and its parameters at a current state can be challenging. For validation purposes and to simplify trajectory programming, an intuitive visualization of context information concerning past trajectory, the goal of the next movement, and effector status is required. Developers need to be able to validate whether the execution of the current program causes the expected effect. For supporting robot programmers in identifying the current state of the robot and possible configuration errors, feedback about current path trajectories or states of different robot parts is required. The second challenge, C2, is about root cause analysis. Enabling a correct root cause analysis of programming errors is important as logic errors may occur when programming. Such errors can lead to unintended actions in the robot behavior. Hence, a common challenge robot programmers need help with is finding root causes for these failures. Problems in source code can be solved if the robot programmer is able to identify these causes for a specific problem. For example, imprecise coordinates or wrong end-effector state at a specific code point. Challenge 3 focuses on vendor robot programming language proficiency. The reduction of needed vendor robot programming language proficiency should also be addressed. Here, the focus lies on approaches using code or code-alike representations of robot programs. Usually, every vendor has its own programming language. Being manufacturer independent reduces barriers to integration. Furthermore, it removes the need to learn a new programming language for every robot vendor. Thus, it probably reduces the mental load when programming and also allows vendor-independent uniform programming. Challenge 4 is about three-dimensional thinking. The correct determination of three-dimensional data is important as robots operate in their own three-dimensional space. A correct interpretation of coordinates and their translation from and into source code is necessary to create working programs. The interpretation can be hard because parts of the robot may have different coordinate origins than the real world. Translating and mapping them to each other is not trivial. Especially 3D models represented on 2D screens cause issues in positioning because of missing depths. Humans intuitively locate things in 3D space and dynamically adapt their estimations as they get closer. Hence, an intuitive definition of targets or coordinates as well as an understandable representation of arbitrary targets are required for simplifying robot programming. As a next challenge, the correct representation of environmental constraints is also very important. For example, when an object the robot might want to grab could be a couple of centimeters off since the last development state. Furthermore, there could be a physical obstacle in the working environment of the robot. Therefore, representing this kind of information as fixtures or cues, as well as integrating them at development time, for example, interacting with a virtual clone of the real object, should be addressed. This is especially important when the recreation of a full simulation for every difference is not possible or a considerable option. Finally, the last challenge is dealing with modification of existing code. When working with existing source code bases of robot programs, it has to be ensured that functional modifications are causing the expected change in behavior. For supporting robot programmers in adjusting and adaptation of existing robot code, it is important to import existing parts of the code and enable a modification in the same manner as the creation of new programs. This, of course, means to consider before mentioned challenges and to reload the modified code to the robot so that the changes in the behavior can be reflected to the robot system. To tackle the previously mentioned challenges, we have developed a novel AR-assisted robot programming environment called Spirit. A general overview of the solution idea of Spirit is shown on the current slide. Spirit is an AR-assisted robot programming environment that supports the different phases of the robot programming process, namely design, build, test, and deploy. In the following, we will describe how we have tackled each of the before mentioned challenges in our solution. To address challenge C1, program state visualization, a head-mounted AR device is used which shows the robot model, its current working state, detected objects, and goals of the next movement. In this context, waypoint drawing and parameter visualization are enhancing the program state visualization. For tackling the second challenge, root cause analysis, the current robot code is shown in the AR robot code panel, so the user knows which code is executed and is able to find errors. By supporting robot simulation, object collision, and code highlighting in the AR-assisted robot programming interface, the complexity of root cause analysis is decreased and gets manageable. To handle the challenge C3, vendor robot programming language proficiency, the code in the AR robot code panel is written in a domain-specific language that is vendor independent. New code can be created, existing code adapted, and both of them executed. This is done by using building blocks. For example, move the robot to coordinate A, enable the end effector of the robot, etc. These building blocks have placeholders, for example, the point A, or whether the end effector should be enabled or disabled. To tackle challenge C4, three-dimensional thinking, these programming building blocks can also be set in the AR environment. The AR environment enables the previously mentioned code interactions as well as some quality of life features, for example, voice commands, transforming the user interface by resizing, rotating, or moving based on gestures, etc. To simplify programming inside the AR environment, the above-mentioned simple and lightweight DSL allows the users to abstract from scenario-dependent settings like speed of movement or movement type. This block-based DSL enables furthermore the user to perform movement tasks as well as changing the state of the end effector. Furthermore, the handling of environment-specific information is handled by object recognition and object interaction. As it can be seen in the screenshot placed in the middle of this slide, specific interaction objects are emphasized. Refer, please, to the detected object, which is the yellow cube. Finally, the aforementioned code creation and modification can be done in the AR application as well as in a non-AR setting using the Blockly web interface. The created artifacts can be synchronized in both directions. Here the translation to the aforementioned block language enables a consistent programming experience for old and new code, so that challenge C6 is also addressed. For the evaluation of the SPIRT framework concerning the introduced challenges, we have conducted remote expert interviews. Unfortunately, due to the current COVID situation, we could not conduct usability tests with a larger group of heterogeneous end users as initially planned. Instead, expert interviews were conducted as semi-structured interviews. We conducted expert interviews with 9 experts from the area of robotics, automation, and augmented reality. For this purpose, each expert received a video for a specific feature of SPIRT and had to answer a predefined set of questions. In the following short demo video, we can see an example video which was used during the expert interviews.
Download. Make.
Inside the interview, a predefined question set was asked to every participant. To derive the questions for the expert interviews, a goal question metric model was used. The evaluation consists of 6 goals. These goals describe whether SPIRT fulfills the respective challenges motivated before. For each goal, different statements describing specific components of the respective challenge were created. Example statements are shown on the current slide. On this slide, we can see the overall results of the evaluation. It shows that the challenges were mostly addressed with a high rating of the experts. Nevertheless, there were some improvement suggestions by some experts, and we will discuss each challenge in the following step by step. The majority of the experts agreed that the AR-based visualization and simulation of the robot helps to increase the understandability of the robot code. Especially the visualization of robot part information, for example the suction cup status, was identified as helpful. Here, one expert concluded that this status shows the potential to integrate other helpful information like current weight load, heat, and motor force. Still, the experts claimed that the current visualization state is not end-user ready and potentially hard to understand without prior introduction. Nevertheless, they see the potential of the approach and believe that further development and better AR hardware will circumvent the current user interface problems. In general, the experts see SPIRT's potential to aid in root cause analysis processes. Especially the smart collision detection feature using the benefits of AR for object recognition and projection facilities was agreed to have potential to improve defect finding. However, some experts noted the fact that some of the existing solutions already provide sophisticated ways of finding software defects through intelligent debugging mechanisms. With this regard, they suggested to enrich those solutions with AR capabilities to combine the strengths of both solutions. The experts expressed that the abstraction from concrete robot code is especially helpful for lay people, as they do not need to learn a new language every time they change the robot. Furthermore, it was stated that the focus on the block-based domain-specific language may also reduce the possible mistakes and ensures a smoother programming process for beginners. Multiple experts, however, stated that they see the advantages mainly in supporting lay people in the programming process, and further, more sophisticated or fine-grained commands could be provided to also support the experts. The received feedback regarding Challenge 4 suggests that coordinate handling is challenging, and SPEART does help in tackling these difficulties with the coordinate selection mechanism and the waypoints drawing. One of the experts stated that problems may occur when trying to select coordinates where different actual combinations are possible. Regarding the challenge 5, in general, the experts agreed that SPEART's object detection has the potential to improve the handling of environmental constraints when doing robot programming. This feedback also shows that the experts see the representation and the integration of environmental constraints into the programming environment as beneficial. The majority of the informal feedback indicates that it is helpful when environmental context information are integrated into the AR programming environment. Hence, the realization of integration of environment-specific information has been considered as a helpful feature for AR-assisted robot programming. Finally, concerning challenge 6, the addressing of this challenge, we received different opinions from the experts. This leads to believe that the experts were not sure about the future or the meaning of the statement. The ambiguity of the statement is also reflected in one expert asking for explicitly stating the meaning of legacy code and its adaptation capabilities in the context of the statement. However, after explaining the meaning, most experts agreed that SPEART offers easy code adaptation capabilities. To conclude this presentation, we have presented an AR-assisted robot programming environment to simplify the complex task of robot programming. In this course, we have discussed the advantages and disadvantages of our augmented reality interface for supporting robot programming. As future work, we plan to investigate the efficiency, effectiveness, and user satisfaction of the SPEART framework based on usability tests with end users from different domains. Furthermore, programming by demonstration could be used to further simplify the programming complexity of robots. Programming by demonstration allows users to program robots by demonstrating a task. Using programming by demonstration for generating source code in the AR framework, which can then be adopted, could allow an even more intuitive way of programming. Thank you for your attention.